I'm very excited that Claire White decided to join us and give us her presentation. Claire is a professor in civil and environmental engineering. She is a material scientist who works in a number of areas, and these include exploring sustainable materials and materials that can help us with carbon capture. Claire has received a number of awards. She has received an NSF Career Award and then the Gustavo Colinetti Award from the International Union of Laboratory and Experts in Construction Materials, Systems, and Structures, which the acronym is RELEM, which includes none of the letters that are in those words. So I'd love to find out how that comes to be. But in addition to these research awards, Claire has a number, 5 commendations for excellence in teaching. So this sort of balance between teaching and research is phenomenal, and we're going to see this, I think, in the presentation today. And then during the question and answer session, we have Maria Garlock has kindly agreed to join us and help lead the discussion. Maria is also a professor in civil and environmental engineering. She's a structural engineer, which is different from a material scientist. Very different. And she looks at resilient and creative designs for extreme loads. And among the extreme loads she considers is storm surge, right? So something also related to the environment. Maria has received also a whole host of awards, recently becoming a fellow of the American Society for Civil Engineers, and also having multiple teaching awards. And she is also the head of Forbes College. So very exciting slate of people today, so take it away, Claire.
Thanks, Gabe. So hopefully everyone can hear me. I've got my mic on and I'm ready to go. So thank you for that very kind introduction. That whole long words actually stands for a French organization, which its acronym is RILEM. So it works out, it just is not equating one-to-one. So today I'm going to be talking about materials for carbon capture, and specifically some very recent work that we've done on some calcium-based sorbents. I must say this is a relatively new area for my research group, so we don't have all of the answers. And also we've been delving into all of the other types of materials, well, learning about all of the other types of materials people are looking at for carbon capture. So in terms of my research group, this is what Gabe went through a little bit. In terms of what we do, we look at blended and alternative cements. That's a really big area of research for my group, whereby we're trying to make concrete more sustainable, specifically by making the material have lower CO2 emissions overall. But we also are working a bit on carbon capture, utilization and storage, and specifically today I'll talk about the carbon capture component. So we focus on the material science of these materials, and we are really at the sub-micron length scale in terms of what we want to understand and optimize, with the idea that that information then can be used for us to understand what's going on at larger length scales and improve performance. We do this both through experiments and simulations across length scales up to the micron length scale. And for cement-based materials, although I'm talking about carbon capture today, I'll just give an example for cement-based materials. If we can tailor the material in terms of its the chemistry and the physics, then we can actually enhance performance at the macroscopic length scale. And that's what we want to be able to do, is predict how these cements will perform in 50 years' time. However, for today, we're going to be concentrating on carbon capture. Forget about cements. So, why carbon capture? I mean, I'm not going to hone in on this topic too much in terms of CO2 levels, but it's very well known that our CO2 levels around the world are ever increasing. And because of this, if we are to limit temperature rise compared to pre-industrial levels to 2 degrees or 1.5 degrees increase, we really need to do something about the CO2 emissions. And so one big component of this is carbon capture, utilization and storage. And a very quick introduction in terms of what this is about. Well, you capture CO2 either from point sources or directly from the air, and then you either store it either above ground or below ground, or people are now talking about utilization, say to make chemicals or fuels. So I write down here on this slide, CCUS is a proven technology. So why aren't we extensively using it around the world? Well, there's a whole lot of non-technical aspects that go into this. I'm not going to discuss them in much detail today, but it talks about carbon tax, carbon incentives, all of these kind of things, because CCUS is not a free technology. It costs money to do this. And one of the reasons it costs money to do this is because the capture stage has high costs associated with it. It's not just the material itself that has to be manufactured that will cost money, but it's also the fact that with these sorbents, with these materials that capture CO2, you need to regenerate them time and time again. And what I mean by that is you need to release the CO2 after it's been captured. So it's this cyclic process that occurs. And with this cyclic process, you need energy to cause the CO2 to be released. Now, that energy might be in the form of heat. There could be waste heat that you can use, but often you need an external source of energy to regenerate the materials time and time again. Now, there's also a whole lot of other technical challenges that people are working on, one of which is, do we have the capacity to store CO2 after it's been captured? And so people are talking about geological sequestration, pumping CO2 underground. There's a lot of challenges there in terms of permeability of the geological reservoir, how quickly can you pump CO2 underground, and people are also talking about above ground storage options as well. So today, I'm just going to be focusing on the carbon capture side of things, and I'm going to go through a little bit of a background as to how it's done nowadays and what are the options people are looking at, and then I'll talk about some of the recent research that's come out of my group. So carbon capture, where are we capturing the CO2 from? There's a number of point sources of CO2 that's associated with different industries. So the main one that people will be aware of is fossil fuel power plants, such as coal power plants. When you burn coal to generate steam in the boiler, then there's a gas stream that comes off from when you burnt the coal that contains a whole lot of different gas molecules, one of which that's in there is CO2, and the CO2 is about up to 20% of that mixed gas stream. So what we need to do is separate the CO2 from the rest of the gas stream, and then once you get the CO2, store it or utilize it. However, it's not just power plants that have CO2 emissions. There are a lot of CO2 intensive industries. For example, the cement industry is one. There's also steel plants. One of the processes involved in steel manufacturing emits CO2 through chemical reactions, actually from the burning of petroleum coke. And then there's also petrochemical plants where CO2 is produced. Now, in addition to these point sources, people, especially recently, have been talking about direct air capture. So in addition to can we capture from these point sources where there's more concentrated CO2 within a gas stream, can we actually capture CO2 directly from the air? And this is being commercialized, and there's been startup companies that have implemented direct air capture in certain parts of the world. And there's an example down here on the right. This is Climeworks, the company, whereby they've got these fans that I'm going to guess, I'm not an expert on exactly their technology, but that's where the fans are being used to blow air through a sorbent. The sorbent captures the CO2, and then they're doing something with that CO2. I think they're pumping underground. So it's not just solid sorbents that can be used for direct air capture. One that people have discussed a lot is hydroxide solutions as a means to, if you flow air or bubble air through this solution, the CO2 will dissolve into the solution, and then you can regenerate that solution and get a pure source of CO2. Now, the last thing I'll mention is this accelerated weathering of rocks. This is not just a carbon capture approach, but it's a way to capture the CO2 and store it. And so olivine, which is a silicate rock, it's naturally abundant around the world, it's magnesium-based, it actually likes to react with CO2. And so people have talked about if you grind up olivine and spread it on, say, agricultural land, over time, that olivine will enhance the absorption of CO2 into the soil, and then that way we are driving down CO2 levels. So there's a lot of different sources in terms of CO2, both point sources from, say, industries, and also people looking at capturing directly from air, whereby we need some kind of capture material to do this. And so I'm going to go through what people have done in the past and what's used nowadays, and then some of the more recent capture materials people have been looking at. But before we get there, I want to introduce the concept, in case it's not at the top of your head, of absorption and adsorption. So there's a difference between these two words up here, whereby if a material absorbs, say, a gas, that means that gas is dissolving into the material. Whereas if a material adsorbs a gas, that means the gas molecules are sticking to the surface of the material. So what's been done in the past for carbon capture has been a lot of absorption-based capture. And so this is where CO2 dissolves into a liquid. By doing that, then you're able to remove the CO2 from the gas stream, and so that's what's been shown over here, whereby if you have a flue gas that contains CO2, here's a liquid, the amine solution. If you pump the flue gas through the amine solution picks up the CO2, and then you've got your gas stream that does not contain your CO2. So the main material that's being used to do this, the liquid, is an amine solution. This is kind of like industry standard, what people are doing. But people have also looked at using ionic liquids and hydroxide-based solutions and others. So once you've captured the CO2, which has been done in this absorber, now we need to regenerate the amine solution because we don't want the CO2 to be in there long term. And so the way that they do this in industry is they use a source of steam, and they heat up the amine solution. The amine solution goes down, the steam comes in, the CO2 goes with the steam, so you end up with a concentrated CO2 source whereby you actually condense out the water, the steam, and then you've regenerated the amine solution. And so this is the process through absorption that is being used in industry right now if they're doing CO2 capture, among other capture approaches. So let's move on and talk about the adsorption. This is a little bit of an introduction. So this is where you have a solid and molecules stick to the surface of the solid. And so the strength of interaction between the molecule, say the CO2, and the solid dictates whether you have strong sorption or weak sorption. And the reason this is important is because that will dictate what energy is required to release the CO2 after capture has occurred. And so if it's a strong type of sorption, often this is referred to as chemisorption, whereas if it's a weak sorption, this is designated as physisorption. And so if we talk about the chemistry here, there's secondary interactions that's causing the molecule to adsorb, which is either van der Waals interactions or hydrogen bonding, whereas over here, if it's a strong sorption, chemisorption, then there's actually primary bonding occurring between the molecule and the surface, and actually here the CO2 has turned into a carbonate ion prior to it interacting with the material. So now that we've got the basis of adsorption for solids, let's go and talk about the current capture options. So I've already mentioned amines as a way of capturing CO2, and this is the most used approach in industry at the moment. Amines are typically low cost, so if you're looking at the liquid, it's about $1 per kilogram as a rough estimate. It's a low regeneration temperature. You're using steam, so that temperature is about 100 degrees Celsius. And there's okay cyclability, which means that you can reuse the amine solution quite a few times prior to it degrading. And so we refer to that as cyclability. Some other things is how much CO2 can actually be absorbed by the material. This is known as capture capacity. It's about 2.5 to 3 millimoles. I know that's a very specific unit of CO2 per gram of sorbent. And why I'm introducing this unit is I'm going to use it throughout the rest of the talk when I talk about capture capacity. The amines are also good at absorbing CO2 from a mixed gas stream without absorbing the other gas molecules, which is good. You want to have good selectivity so that you're not absorbing, say, water molecules and nitrogen molecules and oxygen molecules at the same time. You just want to absorb the CO2. But amines are corrosive. They degrade the capture equipment over time, so a lot of maintenance needs to be done, and they're also toxic. So when we talk about solid sorbents, there's a vast array of them. And I should also say with the liquids, there's also a vast array of the liquids. Today I'm going to introduce to you some of these solid sorbents that people are looking at. Some are implemented in, say, pilot studies. Others are more just being looked at in the lab at the moment. And so we're going to start off on the left with zeolites. Zeolites are crystalline aluminosilicates and they're microporous. So they have really small pores, and if you flow a gas through these pores, you can trap gas molecules. And so that's what they're doing with CO2. They're relatively cheap, about $5 per kilogram. Their capture capacity only goes up to about 3 millimoles per gram, depending on the type of zeolite. There's a lot of different types of zeolites. And the temperature of regeneration is quite low, 100 degrees Celsius, though their capture selectivity is also low. You tend to get other gas molecules being adsorbed at the same time. Recently, metal organic frameworks, or MOFs, as they're called, has become quite of interest to the CO2 capture community. They are more expensive, so at the moment they're not cost competitive in terms of the actual material, but they have a relatively high capture capacity, up to about 5 millimoles of CO2 per gram of sorbent, and a good regeneration temperature. It's quite low at about 100. They also have increased CO2 selectivity compared to zeolites. If we continue going across, calcium hydroxide, for example, one of these metal hydroxides, is a very good capture material in terms of it's very good at sorbing CO2 very strongly, and it has a theoretically very high capture capacity. But the issue with this material is that it requires a really high temperature for regeneration. And so in industry, they're using about 900 degrees Celsius. Lastly, I'm going to introduce layered double hydroxides, and this is what we're going to talk about today, whereby their cost, I've found it's about $1 to $5 per kilogram, but this really depends on the layered double hydroxide material, where you're getting it from, does it need to be manufactured, all of this kind of stuff, so that's why I've put a question mark. Their capture capacity is somewhat unknown, and the temperature of regeneration is somewhat unknown. So let's go and learn about layered double hydroxides, and then we're going to look at the research we've done on these in the lab. So a little bit more chemistry, layered double hydroxides. So these are solid materials that can be used for CO2 capture, among other things. And they can consist of these hydroxide layers. So the white atoms are hydrogen, the red are oxygen, and so that's the hydroxide layer, where there's two metal cations sitting in this hydroxide layer, one that has a 2+ state and one that has a 3+ state. And so that's what's meant by bimetallic hydroxide layers. And in between these layers are what are known as anions, so negatively charged ions that are surrounded by water molecules. So this is the general structure of layered double hydroxides. Now, the nice thing about layered double hydroxides is you can make a vast amount of them in terms of different types. So they're tailorable for specific applications because that 2+ cation can vary. Same is true for the 3+ cation, that can vary as well, and there's lots of options for the anions. So for sorption-based applications, including CO2 capture and, say, sorption from liquids, they work really well because they have high surface area, so there's a lot of sorption sites for the sorption event to occur. And for example, hydrotalcite is one of these layered double hydroxides that also occurs naturally. It's got a chemical formula here. People have looked at it extensively for CO2 capture. The problem with it is it has a low CO2 selectivity and it only weakly physisorbs CO2. So it hasn't really been progressed in terms of looking at its application beyond lab-based studies. However, there's been minimal research on these calcium-based layered double hydroxides for capture applications. And what we're going to find is that there's going to be stronger sorption of the CO2, which changes this mechanism of sorption, which means that we might be able to get higher capture capacities. So the research aim, after that very long introduction, the research aim is we want to investigate the CO2 capture behavior of calcium-based layered double hydroxides. First, we need to make them. These ones are not naturally occurring. So these layered double hydroxides have been made in the past. And the two main approaches for synthesis are shown here on the slide. The first one is solution-based, where you mix 3 different solutions together. And when you mix those solutions together, out precipitates the layered double hydroxide, and then you can filter it from the liquid, and then you have your solid material. The other one is a mechanochemical approach, whereby you take the powders, not liquids, and here it's assisted by a liquid, this sodium hydroxide, and then you put it into a mill, a ball mill, whereby the energy from the mill and the balls moving around at really high kinetic energy means that the powders are being essentially squished together, and the high energy can cause changes in the structure of the material. And so what happens is you transform from having these starting materials into the layered double hydroxide. So these two approaches, it's somewhat challenging to obtain high purity calcium layered double hydroxide, calcium-based layered double hydroxide, mainly because there's a lot of secondary phases that tend to form. And so this is one of the challenges that we've been trying to address, is how can we just obtain the layered double hydroxide itself. And also, sodium hydroxide is not natural. It's a chemical that's manufactured. It's manufactured through essentially electrolysis of salt. And so what happens, it's like splitting of water molecules using electricity. But here you're taking a sodium chloride solution and you're also splitting water at the same time. And out of that comes sodium hydroxide and a byproduct, and it's often chlorine gas, and chlorine gas is not nice to work with. There's also a high energy demand to make sodium hydroxide. So if we're thinking about a material that when you manufacture it, it doesn't have so much concerns in terms of environmental toxicity, we really want to avoid the sodium hydroxide. So what we've been doing is synthesizing these calcium-based layered double hydroxides using 2 different approaches. One is a solution method without any sodium hydroxide in there. It's complicated to try and just obtain the layered double hydroxide, but I'll hopefully convince you that we understand why we can obtain the phase-pure layered double hydroxide. And then the second method is what's known as an electro-deposition method, which is using electricity to make the layered double hydroxide. We've been looking at the mechanism of CO2 capture. We've been benchmarking this layered double hydroxide against other capture materials. And we also want to work on environmental and economic life cycle assessments so that we're not just benchmarking capacity, but we're also able to understand in terms of environmental emissions, energy demand for the material and the regeneration, and also cost. It's very important to keep in mind, if we're synthesizing these materials, what are the starting ingredients that we need to use? And so what you will see here is calcium source limestone, which already has CO2 in it, right? It's a carbonate mineral. So what really comes into play here is if we can get really good cyclability of this material, then that will help offset the fact that when we make it in the first place, we're emitting CO2. Then the other thing to keep in mind is what are the other ingredients that need to be used and where can we get them from? So example, ores, iron ore, alumina, so aluminium oxide, for example. So this will all go into the life cycle assessment side of the analysis. What I will concentrate on today is this synthesis. I hope to convince you that by understanding the chemistry, we know how to create these phase-pure layered double hydroxides. And I'm going to talk a little bit about the recent work we've begun to do on the CO2 capture mechanism and benchmarking performance. So the first method is direct precipitation method, and this work is done by graduate student Maria Curia. And so she's come up with this way to make phase-pure calcium-based layered double hydroxide using the solution of iron chloride, the solution of calcium hydroxide, but no sodium hydroxide. Those are mixed together, the system reaches equilibrium, you filter out the solid, and then you can dry and grind it to obtain the material. And so down here, scanning electron microscope images of the material. So it's got these flat plate-like shapes, but if you zoom in on it, there's this layered structure to it, which is very much indicative of the layered double hydroxide, where these layers for the actual individual particles is less than 100 nanometers. And then if you zoomed in again, you would be out, well, you can't see, but there would be that stacking of the atoms that we saw with the hydroxide layers. And so we can characterize what we synthesize using a technique known as X-ray diffraction. So this essentially, we can look at this and get an understanding of what phases are in there. And so what we see here is if our starting ratio of calcium to iron for those solutions is 1, we don't end up with any of the peaks that have the L on it, which is indicative of the layered double hydroxide. We only end up with actually an amorphous iron oxide hydroxide type phase. Now, if you increase the ratio to 2 for the solutions that you mix together, then you do end up with this peak, which is the layered double hydroxide, but we still have this amorphous phase present. If you go to 3, we're starting to get rid of that amorphous bump that we see, and we still have the layered double hydroxide. If you go up to 5 and 10, we actually end up with what's known as Portlandite, which is one of the starting materials, is still in the system. So we want to be able to obtain phase-pure LDH, and it looks like a ratio around 3 is what we need, but the question is why? I don't have time to go through the details, but it comes down to a lot of chemistry. Essentially, we need to understand what are the aqueous species in solution as a function of pH, because they are the things that come together to form the solid. And so we want to know about those, and we want to also know if there's going to be any solids that form as well. And so for calcium over here, this solid line is indicative of that solid calcium hydroxide, that Portlandite. So we want to stay below the pH at which that forms. For the iron speciation, we know from just our studies that we need to be at a relatively high pH for the LDH to form. And so we actually want to be around this region of this speciation diagram. Note also that this dotted line is a solid phase. So we've got to make sure that there's somehow that we don't have that forming. Sounds like there's some feedback going on. So what happens? This is the chemical equation that people have shown in the past. And so we look at the dominant species in solution that come together to form this layered double hydroxide. And so that's why we're in these regions of these speciation diagrams. The calcium 2+ is the ion, the main ion in solution here. This is a tetrahydroxide ion, which is the main solution species around this pH. And then you've got the other aqueous ions that come together. So the other thing to keep in mind is that these layered double hydroxides with calcium in them are not very forgiving if you have different ratios of this 2+ to 3+ cations. The solid always wants to have a ratio of 2 to 1, 2 calciums to 1 3+ ion. And so that means that when you're trying to synthesize the solid, you have to be very careful with exactly how much you add of each of these solutions, because if you've got too little or too much, you're going to have these secondary phases that form. This is not the case for other layered double hydroxides, such as the magnesium-based ones, which are very easy to obtain with different ratios for the cations that are present. So if we actually do this experiment whereby we go for different ratios for the starting solutions, we can actually measure the equilibrium pH. And that's what these crosses here are. They're experimental results. And then Maria has come up with equations to explain these experimental results, and that's given by the dotted line here. And you can see there's very nice agreement. So if we go back to our experiments and look at what's formed, if we've got this ratio of 1, then the pH is too low for the layered double hydroxide to form, and all that we have is this iron oxide hydroxide phase. If you end up with start with a ratio of 2, we're now in the region where the layered double hydroxide is stable. So we end up with some of that forming, but we still have that amorphous contribution from the iron oxide. And that's because the layered double hydroxide has some solubility to it, so some calcium remains in solution, and there's excess iron, and that iron forms that solid, that amorphous solid. At the ratio of 3, now we've given the system enough calcium so that there's no excess iron in the solution. So this is around the ratio that we want to be, and we have some of the calculations that have the exact ratio that we need to use to get the phase purity. And likewise, if you go to higher amounts, you've got even more calcium in the solution, and your pH is so high that you've formed this calcium hydroxide phase. So now that we've worked out how to make the phase purity, and I should mention why we want to make the phase purity. It's because if you have these secondary phases present, they're going to change your capture behavior. So if you have calcium hydroxide being present, then you're going to be forming calcium carbonate, and that needs a temperature of about 900 degrees Celsius to regenerate. So now let's look at the capture behavior of these layered double hydroxides. So we expose them to 1% CO2, a relative humidity of about 85%, which is quite high, at room temperature for an hour. And what happens is you go from these pure LDHs and you actually form calcite. So this is chemisorption. This is strong CO2 sorption that's occurring. But if we change the relative humidity, so here is relative humidity of 85%, if we change it to 0%, then actually we get physisorption of CO2. So relative humidity is going to be very important, and this is something that we're now studying, is trying to understand at what relative humidity do we get that transition from physisorption to chemisorption. So here is some capacity results. What's shown in green is the amount of CO2 that was sorbed to the material during capture, and so we're between about 3 and 4 millimoles of CO2 for our 2 LDHs. We did also Portlandite, that calcium hydroxide, and actually that has a lower capacity for these conditions compared to the layered double hydroxides. But if you do sorption at 0% relative humidity, you can see how much of an impact dropping the relative humidity has on the capture capacity. So we really want to look at in between these relative humidities. And then looking at the temperature required for regeneration, these bars here give you an idea of the temperature range at which the CO2 was lost from the material when you heated it up. And so if we look in more detail, these are curves that tell you how much CO2 comes off with temperature. So the axis is temperature in the vertical direction. The horizontal direction is the relative amount of CO2. And we can actually see that there's a lot of CO2 that comes off this material at about 600 degrees Celsius for the iron-based one, which is a bit different to the aluminium-based layered double hydroxide. So one thing that we're looking at now is, why is this the case? Why, when you change the trivalent cation, do you get this difference in behavior for how much energy is required for regeneration? But really what we want to do now is look at that impact of relative humidity. We haven't had the chance to do that. I mentioned at the start, this is a relatively new area, so that's something that we really want to look at. We're also interested in understanding the sorption mechanisms in more detail. And we want to play around with the exact type of the trivalent cation, the interlayer anions as well, capture cyclability, selectivity, and so on. So for the remainder of this talk, I'm going to talk about this electro-deposition method that we've used. And so this work has been done by a postdoc fellow in Andlinger, Sean, who's co-mentored by myself and Jason Wren. And so here, what he's come up with is using electricity to do this electro-deposition. whereby we're forming the layered double hydroxide on a carbon fiber membrane. And so the way that this works is you have two electrodes, one of which is the carbon fiber piece of material, the other is platinum, that you immerse into the electrolyte. And here the electrolyte is actually, let's see where this went. The electrolyte is a mix of calcium nitrate and aluminium nitrate. And then if you apply a voltage across the electrodes, you're driving electrons onto the carbon fiber, which is now known as the working electrode, and you have this counter electrode being the platinum. Now what happens near the working electrode, this carbon fiber, is you get reduction of nitrate, whereby you're changing the oxidation state of the nitrate, but you're producing hydroxide molecules, hydroxide ions. And so this increases the local pH around this electrode, this carbon fiber, such that LDH precipitates on top of the carbon fiber. And so the chemical equation is written down here in terms of calcium, and now we're looking at aluminium, and once again there's a tetrahydroxide species that gets incorporated to create your layered double hydroxide. So that's how you can actually directly deposit the layered double hydroxide onto a thin piece of material. And then what Sean's done is done an anion exchange, whereby it's preferential for chloride ions to exchange for the nitrate ions, and therefore you can end up with calcium aluminium chloride layered double hydroxide. So if we have a look at some electron microscope images of what things look like at the various stages of deposition, what we see here is that this is the starting carbon fiber. After the deposition has occurred, we end up with these flat plate-like sheets that are indicative of layered double hydroxide, and after the anion exchange, we end up with slightly different morphology, but we still have those plate-like sheets that are indicative of the layered double hydroxide. Now, by playing around with the current density that's applied during electro-deposition, we can change what phases are present. And so in addition to the layered double hydroxide that forms, we have been getting secondary phases that form. And this can be, this can be explained by what I was discussing previously in terms of the impact of pH and the relative ratios of the different cations. And so what we see here is for a low current density, we end up with a layered double hydroxide, which are the diamonds, and then the secondary phase is aluminium hydroxide, which is the upside down triangles. If you increase the current density for synthesis, you end up with your layered double hydroxide, but now the secondary phase is calcium hydroxide. And so what that means is during the deposition, using this current density, that the amount of hydroxides that were being produced were high enough so that the pH was above the pH at which calcium hydroxide precipitates. And so even higher current density shows this calcium hydroxide forming as well. So it's likely possible, and this is what we're still working on, possible to tailor current density to avoid formation of these secondary phases. This is just kind of a first approach of the deposition by changing the current density here. So we want to understand, we've made this material, how does it behave in terms of CO2 capture? And so one thing that we can do is, after we've done the capture itself, these are the conditions that we use for capture here, we can heat the material up, watch how much weight it loses as you increase the temperature. And so that's what's shown on this diagram. In the grey, the red is the derivative of the grey. And down here is actually infrared spectroscopy data that shows us what type of gas molecules are being lost at which temperature. And so this is how we can work out exactly what temperature is required for regeneration through these signatures of the different gas molecules being lost. Now, what we've done here is, if you heat to 300 and hold for a period of time, then this is how much CO2 has come off the sample. If we heat to 400, go from 300 to 400, this is how much CO2 comes off, and so forth, where the weight corresponds to the CO2 released. And therefore, we can benchmark what is the capture capacity of this layered double hydroxide. And what we find out here is about 3.5 millimoles of CO2 per gram of the sorbent. Note here that because of the overlapping regions of CO2 and water for both of these layered double hydroxides, we've only looked at what comes off the sample above 300. We still need to quantify how much CO2 is coming off at lower temperatures. Likewise, here 50% relative humidity, so we are still getting chemisorption at this relative humidity. It'll be interesting to look at lower relative humidities and how that changes capacity and regeneration of the material. 2 slides to go and then I'll be done. So we've also looked at the impact of relative humidity and temperature on the capture capacity of this layered double hydroxide. Specifically, now we're looking at the anion exchanged one. And so what we see here is that if you have humidified CO2, about 60 to 70% relative humidity, we've got a capture capacity of about 4 millimoles of CO2 per gram of sorbent. Whereas if you have dry CO2, then the capacity has significantly reduced. And so once again, we're really interested in looking in this intermediate range in terms of relative humidity to see if we can get more sorption of CO2, but a lower energy requirement for regeneration. And as you see, in terms of adsorption temperature, you want to adsorb at room temperature because the higher temperature you go up, the less absorption you get. So if we take this 4 millimoles of CO2 per gram of sorbent and plot that in the orange star, that is what we got in terms of the capture capacity of our layered double hydroxide. And what's shown on this slide is other capture materials and how much they've captured in terms of carbon dioxide as a function of partial pressure. And so what you see here is those MOFs, metal organic frameworks, tend to be the best performing, though mind you, there's some down here. It really depends on the exact chemistry of the materials as to how they perform. The zeolites are here in the red, activated carbon is here on the right, and then there's these amine grafted materials as well that have intermediate types of capture capacities. So you see that we're doing okay in terms of capture capacity of this material, but the energy of regeneration required is on the higher side. Last thing in terms of cyclability, we did a study on cyclability using what's known as Joule heating as the regeneration approach. And this is where you use an electric current to heat up a material. And because the carbon is conductive, that means that the carbon heats up and the layered double hydroxide heats up at the same time. And by tuning the power, you can change the temperature at which the system's heated up to. And so we did this a number of times after the carbon dioxide was captured. And this is what we can see in terms of the behavior. You do get a slight decrease in the amount that's captured as a function of number of capture cycles. And this is very typical of sorbents, whereby you are getting some changes occurring, which is going to effectively decrease your capture capacity to some degree. But here, the decrease is on the order of about 15%, so it's not too bad. We haven't dropped by a third, for example, after 10 cycles. And then what's shown here is how quickly the CO2 comes off during regeneration, where each of these green parts is about five minutes long. And so you see within the 5 minutes, a lot of CO2 comes off right at the beginning, and then some of it's coming off later on, where if you held for longer, more CO2 would come off. But within 5 minutes, we saw that there was a good regeneration of the material. So in terms of future work, it's very similar to the previous area in terms of we want to understand capture mechanism, the impact of the relative humidity. Here we want to quantify how much CO2 is coming off below 300 degrees Celsius. We want to do extended cyclability tests, and we want to do the LCAs in terms of environmental and economic aspects. So this was a very quick kind of introduction to the types of research we're doing on CO2 capture in my group, whereby we're looking at these solid sorbents. They show some promising behavior in terms of CO2 capture. The main drawback to do with these solid sorbents is the high energy required for regeneration through the need for high temperature, but maybe depending on the relative humidity at which capture occurs, this could be a balance in terms of requiring less energy for regeneration. And it should be mentioned that when you look at these flue gases that come off point sources, they tend to be on the lower side for the relative humidity. And likewise, when it comes to direct air capture, the relative humidity is dependent on the part of the world that you're in, the current weather that's going on, all of this kind of stuff. So it's probably not a material that you want to use in Singapore where it's very, very humid, but in more dry climates, this type of material might work well as a direct air capture material. And lastly, in terms of the actual synthesis of the materials, we've now been able to work out how to precipitate phase pure layered double hydroxides, and also using this electro-deposition technique. So I think there's promise to do with these materials with CO2 capture, but there's a lot more research that needs to be done before it can be implemented into, say, pilot studies, that side of things. So in acknowledgement, the researchers who actually did this work was Maria Curia and Sean Zheng. Funding came from seed funding from the NSF MRSAC on campus, and also the affiliates funding from Andlinger Center. I'd like to thank all of my students and postdocs, and I'd thank the audience as well, and be happy to take any questions.
Thank you, Claire. That was a great presentation, and I learned a lot. As Gabe said, I am a structural engineer, and the chemistry is maybe beyond my knowledge, but the work that material scientists do are so important to the field of structural engineering because we work with steel and concrete, and we want to do this without having such a huge impact on society. So this research is really important. And you mentioned in the beginning that there were some barriers to overcome with carbon capture, and you mentioned things related to policy and politics. But that aside, as engineers, I think we're responsible for bringing forward ideas that are efficient and economical. So I'm going to ask you a question related to efficiency and economy as related to your innovation. So from the point of view of efficiency, if I understand right, to get calcium, you need to get it from limestone. You have to heat the limestone, which releases CO2. So can you talk about the efficiency of that process?
Yeah, so when it actually comes down to the capture material itself, it's really the number of cycles that you can do capture before the material essentially has lost its capture ability. And so the efficiency of the material in terms of this capture, really you'd need to, I think I've got the mic still on. Yeah, I still have the mic. Really, you'd need to do very extensive long-term cyclability tests because if you can only use this material to capture for a very short number of cycles, then really you're not going to get any benefit from doing capture using this material, given that the actual synthesis itself has CO2 emissions associated with it. But this is the case for all capture materials, essentially. Is when you manufacture in the first place, they've got energy demand, they've got CO2 associated with them. So really it comes down to the cyclability as to whether there's a benefit overall in terms of CO2 emissions, for example, or energy, those kind of things, where the most efficient sorbents will be the ones that should be implemented in practice.
Okay, thank you. And then the question of economy. Can you talk about the economy of your innovation relative to the others, for example, that you presented in the beginning?
Yeah, so in terms of economics, there's two aspects: the cost of the material itself to manufacture, and then essentially the energy demand for regeneration, because the energy has to come from somewhere. It might be electricity, for example, or it might be heat. And so that's aside that we're still hoping that, well, not hope, I should say, that we're still to find out if regeneration can occur at a lower temperature for a lower relative humidity. But when it comes to the actual cost of the material in the first place, calcium carbonate is dirt cheap. It's used, for example, in the manufacturing of Portland cement. And Portland cement, you can buy it for about $100 per ton. So calcium carbonate is a relatively cheap to purchase or to get. It's going to be the other elements that need to be incorporated into the layered double hydroxide that will essentially dictate the material cost. So hopefully, I keep on saying hopefully, I need to stop saying that, we'll find out what the economics will be like, whether it's competitive or not.
Research in progress, that's fair. Okay, thank you. All right, so I will take questions from the audience, and I'll repeat it here so that the people on Zoom can hear your questions. So, and we have one question in the Q&A. Anyone else online, please go ahead and post in the Q&A. Any questions? Yes?
Yeah, so you looked at efficiency over a range of relative humidities and temperatures. So I was just curious to understand better from maybe the chemistry perspective why you expect relative humidity to be a better variable than just like the absolute humidity.
Okay, so the question was why relative humidity as a variable is something to look at, say, compared to, you were saying, absolute humidity?
Yeah, it just seems sort of complicated to look at temperature and relative
humidity. Yeah. So what we know, well, the impact of temperature, as we saw from the slides, the higher the temperature, the lower the capture capacity. And so that's, if you've got sorption going on, the higher the temperature, the more kinetic energy that the gas molecules have, the less likely they are to stick to a surface. So that's the temperature side. When it comes to relative humidity, this is not fully understood when it comes to, say, carbonation of calcium hydroxide, but the thought is you need a certain amount of water to be absorbed to the surface of the solid so that the CO2 is actually somewhat dissolving into the water, forming carbonates, and then it's the carbonates interacting with the surface of the solid. And so the higher the relative humidity, the easier it is for the CO2. There's more water around absorbed to the surface, so the CO2 has a more likely chance of first being incorporated into the water, and then if it's undergoing the conversion into carbonate, going through that process. The lower the relative humidity, the less water layers you have on top of the solid, so that process is less likely to occur. This is more of a hypothesis at the moment in terms of these solid calcium-based materials for the CO2. In the cements world, the process of carbonation through chemisorption is CO2 dissolves into water, forms carbonate-type molecules. The pH drops, the solid starts to dissolve, and you form these calcium carbonates. But it's still to be seen when it comes to these capture materials, what is the actual mechanism of capture. So that's why, it's a long story, that's why relative humidity is important, because it really dictates what the CO2 can do at the surface of the solid.
Thank you. So why don't we take one online question? I think you answered the first question and you could see the others. Go ahead and pick one.
Okay, so the first one I actually just answered in terms of relative humidity. There was a question on relative humidity. There's a question from Satish Maineni, Professor Satish Maineni, that says if calcium carbonate and calcium hydroxide are used in the making of LDH, they are going to release CO2 in the process. Hence, what is the advantage of using these in capturing CO2? Thanks, Satish. So here I'll reiterate, it comes down to how many capture cycles can you perform using the layered double hydroxide. Because what you will find is that the manufacturing of the material in the first place does emit CO2. A lot of the other materials that are synthesized to do capture do the same thing. However, if then you can do capture, release, capture, release, capture, release, capture, release for a very long time, then it's an efficient capture material. When it comes down to why are you using a carbonate material in the first place to do this capturing, the important thing to keep in mind is the number of cycles you can get out of the capturing. I should say there are processes that I didn't talk about today. One is such as calcium looping that people have been talking about putting on power plants and cement plants, whereby you're actually taking calcium oxide and reacting it with CO2 to form calcium carbonate, and then you heat it up, drive off the CO2, so it's in a pure CO2 gas stream, and then you recycle the calcium oxide and you do it again. So that's another example of where calcium carbonate is being used for a capture and release process. And that's seen as industry is implementing that at the moment, so it's seen as economical. There are some issues when it comes down to sintering of the calcium oxide particles, so they become less efficient over time, but it is this cyclic process that occurs. And so in a similar way, although the layered double hydroxides don't contain CO2 themselves, the starting material, one of the starting materials does, but if you look at the overall process, what you find is that the amount of capture that you can do using the material is quite high. If that's the case, then it's good capture material. And so even though you're starting with a carbonate material in the first place to make the layered double hydroxide, it's offset by the efficiency of the actual capture material.
Thank you. Gabe, do we have time for one more question? All right, one more question from the audience. Yes, go ahead.
I wanted to just ask about cyclability, because it seemed like you had a little bit more to say on the second method of manufacturing than the first one, and so I was just wondering if you had any sense of, or guess for why it might be different between the two methods based on like the structure you can see on the X-rays or the temperature produced or something.
Okay, so that question was about cyclability, and we did that on the electro-deposited layered double hydroxide. We didn't really talk about that on the solution-based one. That's just because we haven't done cyclability studies on the solution-based layered double hydroxide. It's probably going to have a similar behavior as the electro-deposited material. It's less about one only works less in terms of it's less cyclable than the other. It's not that, it's just we haven't done the studies on the first one in the first place.
All right. So, looking at time, or should we take another question? Do we have one more question?
Yeah. So I'm thinking on this cyclability problem, and you discussed earlier on that you have the chemi-sorption and also the fizzy-sorption. And it looked like the fizzy-sorption absorbed a lot less CO2, but the temperature with which you could produce the CO2 out was much lower, in my mind.
Yes.
So I'm wondering whether you've been able to look at the fizzy-sorption mechanisms, and whether you could also play around with delaminating the pHs without playing around with temperature so much. Whether that's a fruitful way to go forward.
Yeah, so I'll just repeat the question for the audience that's online. So the question was, although fizzy-sorption had less capacity, the regeneration of the material after CO2 was fizzy-sorbed would be less compared to the temperature required if you get chemi-sorption of CO2. And you've hit the nail on the head in terms of why we're trying to look at the relative humidity, because the hope is by looking at the impact of relative humidity, we can tailor between fizzy-sorption and chemi-sorption. So we can bring down the strength of the interaction through decreasing the relative humidity. We won't have such a high capture capacity of the material, but we'll have a lower energy requirement for material regeneration. And then the second part of the question was about if there's other ways you can play around with the material, potentially for desorption or these kind of things, if I got the question correct. With these materials, you can have different entities within the interlayers. And so potentially you could change the capture capacity and the material regeneration temperature by, say, changing the interlayer anion or shoving big things between layers, these kind of things. very important areas, things we have yet to have a look at.
Okay. So, looking at the time, I'm going to take the mic. And first, I'd like to welcome all of you to thank Claire and Maria again for a wonderful discussion. I'd like to thank you for coming and joining us physically and virtually. And I'd also like to thank all the production crew that has worked so hard to make this work in this mixed virtual real life setting. Thank you so much. And I will remind you that on October 5th, we have Tina Gerhardt is our Barron visiting professor, is going to be giving our next seminar. So look for the invitation to that, and I'm looking forward to seeing you then. And thank you again.